Welcome to the Smart Salting Enhanced Winter Maintenance Equipment Calibration Training video. My name is Jason Swope. I'm an instructor for the Maryland Department of the Environment Smart Salting Program. During this video, we will be reviewing the calibration process for equipment that applies granular and liquid ice melters. Equipment calibration involves measuring the amount of chemicals applied to a known area at varying equipment settings and speeds over a specified time. Calibration of all winter maintenance equipment, including vehicle-mounted spreaders, manual spreaders, and sprayers, is an essential component of the smart salting concept. It should be done annually before the start of the winter season to ensure accurate application rates. Proper calibration allows for better tracking of materials and prevents over-application, which can reduce costs and minimize impacts to the environment while still maintaining public safety. The key to determining application rates is to know how much material is applied over a known area. Once we have this calculated, we can multiply by 1,000 and our application rate will be in pounds or gallons per 1,000 square feet. This is our guiding equation: the amount of material applied divided by the area of application times 1,000. Depending upon the conditions, the ideal application rates are 1 to 3 pounds per 1,000 square feet for rock salt and about 0.3 to 0.8 gallons per 1,000 square feet for salt brine. The range of application rates are based on surface temperatures and weather conditions. These de-icing and anti-icing application rate guidelines can be found on page 15 of the Enhanced Winter Maintenance Training Manual Charts and Forms Addendum. Today, we will be looking at the calibration process for a walk-behind push spreader, a brine applicator, and a truck spreader. Application rates will vary based on the flow of materials to the spinner or spray nozzles, which can be adjusted by the operator. The operator may also be able to control the width of the spray pattern by adjusting the spinner speed. For push spreaders, the width may vary based on the speed which the spreader is pushed, so it is important to walk at the same general pace when performing the calibration of push spreaders. We will be using the worksheets provided to you to record the application area and the amount of materials applied at different equipment settings. The goal is to use this information to create an application chart for the equipment operator to refer to when applying materials. Let's first take a look at push spreaders. Again, what we are seeking to do with the calibration process is to determine the amount of material applied over a known area at different settings on the spreader. The settings on the spreader allow more or less salt to flow to the spinner, which will change our application rate. The calibration process is straightforward, but it must be repeated for each spreader setting that you choose. You start by filling the spreader with the product that you plan to apply. Then, starting with the low setting, you will apply ice melter over a known area. For our calibration process, we used a blue tarp that was 30 feet long by 19 feet wide. With each application, we maintained the same walking pace and applied the ice melter evenly over the entire area. After each application, we collect and weigh the material applied and record that information on our calibration worksheet. Here are some images of how this process works. Our tarp was 30 feet by 19 feet, so we know the area is 570 square feet. For each spreader setting, the ice melter material was applied evenly over this area and then swept up, weighed, and recorded. For the push spreader, we selected settings 5, 10, 15, 20, and 25 and performed the calibration process for each setting. To ensure accuracy, it would be best to repeat this process several times per setting and use the average rate. This information is recorded on our calibration worksheet for push spreaders. Again, our guiding equation is pounds per square feet multiplied by 1,000 to give us pounds per 1,000 square feet. Here is the guiding equation and solution for setting number 5. At that setting, we applied 0.45 pounds of ice melter over an area of 570 square feet. Here is the guiding equation and solution for setting number 25. At this spreader setting, we applied 2.4 pounds of ice melter. You can repeat the calculation process for the additional settings using the data for each. And I would encourage you to do so to make sure that you understand the math. However, the spreadsheet provided will do the calculations for you based on the data inserted into the yellow cells. On all of the calibration worksheets, yellow indicates an area where you enter information that will then be calculated. On the worksheet, click on the Push Spreader Calculator to see the calculated answers. Next, we'll look at the calibration process for a brine applicator. For the brine application machine, we are working with a liquid deicer instead of a granular product, so our measurement will be in gallons instead of pounds. But the calibration process is still the same. We want to determine the amount of material applied over a known area, in this case, gallons per square feet. You will notice on our calibration worksheet that in addition to the amount of material applied at each setting, we will also need to record the boom width, number of nozzles, and the static pressure. To calibrate a brine applicator, we will measure the volume of the material discharged from one nozzle in 1 minute, starting with a low setting and repeating the process for progressively higher settings. During the calibration process, we recorded the gallons discharged from one nozzle in 1 minute on the brine worksheet. Here's an image of the brine applicator being calibrated. During the calibration process, we are using water instead of brine. The area of application in 1 minute will depend on the width of the boom and the speed that the truck is traveling. On our brine worksheet, distances traveled in 1 minute are provided for 5, 10, 15, and 20 miles per hour. Here is our guiding equation and solution for setting number 1 at 10 miles per hour. For material applied, remember to multiply your volume recorded by the number of nozzles, in this case 7 nozzles. To determine the area, multiply the distance traveled in 1 minute by the boom width, which in this case is 8 feet. At setting number 1, 0.33 gallons were discharged. We multiply that by 7 since there are 7 nozzles on the brine applicator. For the area, our width is the width of the boom, 8 feet, and our length is 880 feet, which is the distance of travel at 10 miles per hour. By multiplying length by width, we can determine our area. Here is our guiding equation and solution for setting number 3 at 15 miles per hour. For material applied, remember to multiply your volume recorded by the number of nozzles, which is 7. To determine the area, multiply the travel speed by the boom width, which is 8 feet. Because the truck can travel at different speeds, the application area changes, so you will need to perform several calculations for each setting. Here we have 4 settings at 4 different speeds, so that would be 16 separate calculations. Fortunately, the brine calculator tab of your spreadsheet will perform the calculations for you based on the data entered in the yellow cells of the brine worksheet. The last piece of equipment that we will look at today is a truck salt spreader. To calibrate the truck spreader, there are 3 factors that we will need to consider. The spinner speed is variable and will affect the width of the application area. The truck speed can be variable and will affect the length of the application area. And the auger speed is variable and will affect the amount of a material applied. However, again, the calibration process is still the same. We determine the application area and the amount of material applied in the application area, and then multiply by 1,000 to get pounds per 1,000 square feet. In this photo, we can see the truck spreader is in position over the tarp so that when we turn on the salt spreader, we can measure the width of the application at various spinner settings. For this calibration, we selected spinner setting 20, 25, and 30, and recorded the width of the application for each spinner setting. The salt on the tarp, we perform a similar process for several different auger settings by collecting and weighing the amount of material applied for each auger setting. For For this calibration, we selected auger settings 15, 20, and 25 and weighed the amount of material applied for each auger setting. Because the width of the application area can change based on the spinner setting and the length of the application area can change based on the truck speed, we will need to calculate the application area for each spinner setting at each rate of speed. We have recorded our spinner setting widths, and we are given the length of travel in 1 minute for speeds of 5, 10, 15, and 20 miles per hour. Therefore, we will need to perform 4 area calculations for each spinner setting. Each calculation will be for a different rate of speed at that specific spinner setting. These are the area calculations for the 3 spinner settings at 10 miles per hour and 15 miles per hour. Now we are ready to perform our final application rate calculations for the salt spreader by using our guiding equation. We have determined the areas based on the truck speed and spinner setting, and the material amount was determined from the data we collected during calibration. The calculation shown is for 10 miles per hour, number 20 spinner setting, and number 15 auger setting. You can refer back to the previous slide to see how the area was calculated. The amount of material applied comes from the data we recorded on our truck spreader worksheet. This application rate calculation is at 10 miles per hour and auger setting of 15, the same as in the previous slide, but the spinner setting is set to 25. The new spinner setting will change the application area, which then changes the application rate. Compare the results of the 2 previous calculations. Changing the spinner setting from 20 to 25 changed our application rate from 3.9 pounds per 1,000 square feet to 1.8 pounds per 1,000 square feet. This application rate calculation is at 10 miles per hour and a spinner setting of 25, the same as in the previous slide, but with an auger setting of 25. The new auger setting will change the amount of material applied, which then changes the application rate. Compare the results of these 2 previous calculations. Changing the auger setting from 15 to 25 changed our application rate from 1.8 pounds per 1,000 square feet to 2.6 pounds per 1,000 square feet. As you can see, with 3 variables, there are a lot of calculations to perform in order to determine the application rates for the various combinations of truck speed, spinner setting, and auger setting. Fortunately, the spreadsheet provided will do the calculations for us based on the data entered into the yellow cells. If we enter the auger and spinner data collected in the field in the truck spreader worksheet, and then enter the truck speed in the truck calculator worksheet, the applications rates will be calculated for us. You will need to print a worksheet for each of the different truck speeds so that you have application rates that account for all 3 variables. Shown here on the right are the application rates for the truck spreader at 10 miles per hour. And here we have shared the application rates for the truck at 15 and 20 miles per hour. Providing these application rate charts to the equipment operator will help them to determine what settings to use to achieve the desired application rate for the weather event and their speed of travel. In summary, as you perform each calibration activity, you will need to record your results in the highlighted areas on each of the worksheets. Each piece of equipment has a print tab on the worksheet so that you can print the worksheets for use in the field. After you've completed the calibration process in the field, you can input the data recorded into the worksheet on your computer and then print the resulting calibration charts that are calculated. Thank you for taking the time and effort to attend the Maryland Department of the Environment Smart Salting Certification Training. If you have any questions about the calibration process or any of the material covered in the manual, e-learning modules, discussion forums, or in the calibration training, please feel free to reach out to me by email, jason@cblpro.org. Good luck on the final exam and best wishes for a safe winter season.